So today we are conducting a battery webinar series where our first part is introduction to battery. So what are the batteries and how we can perform the thermal analysis of a single cells. Same way we'll do the part 2. Part 3 we will cover the battery pack also. So our agenda for today will be like we will introduce about the ANSYS already you have seen in the video. Then what tools we have in CFD bundle. So because battery comes under the CFD tool bundle. So what other advantage you can have when you are working on the battery, other physics you can solve. Then we'll talk about the batteries and its application. Then how ANSYS provides solution for battery different designs and how we can perform the simulation. Later on, we'll do hands-on on two workshops on cylindrical cell as well as on the prismatic cells. And in the last, I will show you how we can learn this battery kind of simulation, what are the learning resource and what kind of courses available on ANSYS website platforms. Okay, so as you're already familiar with the ANSYS, from last 50 years, ANSYS is unlocking lot of capabilities. We are seeing a lot of challenges in the battery market also. So how to overcome these kind of challenges? We can perform the simulation instead of doing the practical. So ANSYS is a simulation company which provide complete solution for all kind of different complex designs. And from last 50 years, we are trusting our companies. How we are building those trust through R&D. So in R&D, all these big giants companies, they are using ANSYS to develop the products. So overall, we can say if we see in the medical fields, it saves a lot of life. Even if we talk about the simulation of aeroplane, like how we are able to increase the lift and we can carry more passenger, the network system 5G. So different physics. So ANSYS is all over the physics, mechanical, civil, electrical, electronics. So it's play very important role nowadays in academic part also, where we can teach student the real physics behind that part. Now we'll come to the CFD part. CFD is like computational fluid dynamics to predict the fluid flow, heat and mass transfer, chemical reaction and other related phenomena. To solve this CFD, we solve our equation like conservation of mass, conservation of momentum, energy equation. So based on the requirement, we solve this kind of equation. Where we has come to battery, we solve our battery equation. When I'm looking for the cooling of battery, then CFD also play a very important role. How my fluid is taking away heat from the batteries and how it will go, whether I am doing liquid cooling or the PCM cooling. So depends on the how my PCM will be surrounded. So all those concept we'll also study. Just will take overview of today, but in upcoming webinars we'll cover those aspect also. So CFD, we know it provide complete flow behavior, distribution of pressure, velocity, temperature. For external flow, we can simulate our lift and drag. So it's battery not only like which is placed inside a car. If we have the drones, other things, so we should know how much size I should keep for my batteries. There, the battery weight will have the effect on the lift and drag. So when you're simulating a drone, so the lift and drag play also important role. So it's not only you're simulating battery, but sideways efficiency also have the better, because when you're doing external flow simulation, we may have to cool our battery also. So how I can take that cooling air without increasing more drag. So that kind of simulation the engineers are working on the drone case side. Then we have distribution of multi-phase phases, like when we are extracting oil from the ocean, so we can perform those kind of simulation also. Related to combustion part, we have different chemical species which are reacting. So nowadays we are going towards greenhouse gases, how we can reduce those greenhouse gases. So how the combustion I can have better efficiency. So those kind of hydrogen combustion performance we can check with the CFD simulation. There much more. So and in industries as well as when we are doing R&D, we study CFD in various aspects of pillars. Like when in academics we study the conceptual studies, how what is the basic principle of conservation of mass. So we say contained equation, Navier-Stokes equation for the momentum equation. Same way when looking for the energy law, energy can neither be created nor be destroyed. So those study in the energy equation. So like this we have to perform the behavior. I will just put the pointer. Okay, then we are developing some product also. Like if we take example of battery, now I am making my battery, I am packing my battery cells, I am making a module. From that module I will create a battery pack. So I could have different kind of series, N series, in series form, then in parallel form. So how I can create a complete product. by seeing a lot of external factor. So those we'll discuss in upcoming slide. But complete development also plays very important role. So CFD help us to develop a complete product. Now already we have design. We have seen there already scooters are coming, bikes are coming, cars are coming. Now we have to optimize. Nowadays what we are facing issue, the range. We are not getting that much range. So how we can increase the range without adding that much battery size. So that optimization process also we can do even by reducing the weight. So what kind of batteries chemical property we should have, so those kind of optimization we can also find out. Then next part is troubleshooting, that is very important. So you can might have seen a lot of time there is a explosion. So why that explosion is coming, when there is a leakage, so why the leakage is coming. So those kind of design we can also perform in the CFD simulation, and we can identify the main cause of the problem. And if you want to design overall redesign any concept, we can redesign the our battery simulation also. So it's not about battery, complete anything where there is a fluid flows, we can predict the CFD analysis through and identify the major cause and advantage of the design. If we talk about CFD products, so in academics we have these bundles. So Fluent is the general purpose tool for CFD analysis, where 98% industry use Ansys Fluent for basic CFD analysis, whereas for specialized application like turbo machinery part, then we use CFX part. So if for battery simulation, we can perform in some people think that battery is a part of electrical team or electronics team which are working. But most of mechanical engineers are working on the batteries due to their thermodynamic subject efficiency, due to their heat transfer concept studies. And batteries are solid in nature. We might not work in the chemical behavior, like how the chemical composition will be there, but we can understand and we can learn. So in industries, there is a team who works on the chemical composition, or like they find out the where it will be fitted, what will the voltage will be there, and how the composition will be there. Then they don't know like how the heat will transfer, that it will explode or no. So there comes the thermal engineer, which plays very important role. So we study that behavior in Ansys Fluent. If you want to go for further simulation, like with respect to other specialization in turbo machinery, you can go with the CFX, which works on the rotating components, turbines. So you can see plane around us, wind turbines. So we are optimizing those performance with the help of CFX tools. Then we have Rocky tool. So this is the good news for the academics. So Rocky is recently added in 26 version, which along with the CFD bundle. Earlier it was a separate bundle, separate tool with additional cost, but now it is part of our CFD bundle. So Rocky is a tool where we study about the particle behavior, how the particles are moving or when it interacts with the fluid. So you can take example in coal and mine area. When I'm breaking coals and transferring through the conveyor belt, so in what size I should break, how will I transfer it through wagon wheels, so in what quantity or what speed I should fill that coals. So I can study the particle forces, I can study the particle movement. So related to those we study inside the Rocky. And after merging, earlier Rocky was a separate tool, but after merging with the Ansys, we can couple with the Ansys Fluent and we can study the behavior. So in if we talk about the battery, so battery cleansing for battery manufacturing industries, they are treating the battery particles in to manufacture the battery. They use Ansys Rocky for the battery manufacturing. So there is a complete application of Rocky. I'll show you in one slide at the end. So how Rocky is useful for battery engineers also. Then next we have Ansys Forte, which is specialized tool for the combustion process. Next we have ChemGen Pro, specialized tool for chemical engineers who want to work on the reactors or chemical reaction. So in general, we can solve some 50 reaction, 15 to 20 reaction in Ansys Fluent related to combustion. But if I have a lot of reaction, more than 100 or 500, and there is a complete flow diagram of number of reactors, because in chemical industry we see lot of reactors are there which are connected. The chemical will come from one reactor, it will pass to second reactor. So those kind of network I can develop in the ChemGen Pro, and I can simulate the complete chemistry behavior of the reactors as well as reactions. I can identify how the heat will be generated, or if we have to add the heat generation. So those kind of thing we study in the ChemGen Pro. Next we have FanSap Ice, which is tool related mostly for the aircraft. Even in the drone cases nowadays, we are seeing drone are going above cloud height. So when any object which interact with the clouds, because in cloud what we have super cooled liquid. So as soon as it touch with the any solid substance, the ice will form. So you can see in the figure also the ice is forming. So due to this ice formation, what will happen? The lift will reduce and the drag will increase. And same ice will go to the turbine also, where it will melt and it will cause a rusting. So those every aircraft have to go with the anti-icing aircraft certification. So we predict this icing behavior with the help of FenSAPI. So you can see it is not easy to do the testing in the cloud with the cloud. So through simulation we also predict, and we have to create same kind of, so the making that kind of experimental is very costly. That's why we prefer the simulation part. Then next we have Insight, which is advanced post processing tool. So you can see in this we are seeing some color contours, like, okay, which is showing the pressure or the velocity. Same way, if you want to animate anything which is realistic, like water is impacting on the pillar, so how much turbulence it will create, or what are the pressure value will change, or how is kinetic energy is changing. So those prediction we can study in the uh, post processing tool in the Fluent as well as in the Insight. So Insight gives more advantage of control over the post processing part. So Insight is enabled for mechanical as well as for CFD and other CE Ansys tool. Then last we have Polyflow, which is widely used for the plastic industry. So how we are creating the mold, and from the mold how we can reduce the wastage. So mostly our CPET Institute plastic industries, they are using Polyflow tool to reduce the wastage of our mold design. Mold design we generally do in the NX, but to predict how the mold will create the simulation, how the thing will happen, like glass molding process, blow molding, forming process, all those process we can study with the Polyflow. So these are our solvers CFD products. So if we talk about what is the process to simulate, what we should have, first we should have model. So we can create model in any CAD tool, or we can create in our Ansys CAD tool also, that is Ansys Space Claim. We have Ansys Discovery and Ansys Design Modeler. Nowadays industries are moving towards the Discovery, but initially level the user interface same only, Space Claim and the Discovery, but we required some graphic card, good GPU to run in the Discovery part. So mostly in academics we are seeing Space Claim is widely used by the students. It gives better hands-on control to create our models or to import any CAD model. Then we have to repair our CAD model if we are importing our CAD model. Then we will convert this CAD model into mathematical model, where we have the meshing, different technology like meshing, fluent meshing, TurboGrid and ICM CFD. For battery simulation, we can prefer workbench meshing as well as the fluent meshing. Whereas for specialized application like turbines, we use TurboGrid. So if we require have complete control on the mesh, where the geometry is even complex, like you can see there's a lot of curvature in the aeroplane design. So in this other techniques, the algorithm will play important. So based on the shape, the algorithm will decide. Whereas in ICM CFD, we can control each node and elements, and we can create complete structured mesh. Whereas these tools, based on the shape of design or method, we can control, we can design the meshing with whether it's a structure or unstructured mesh. Now, once I convert my CAD model into mathematical model, then I have to transfer to solve our equation on with respect to our physics we required. So in solver, we select the solver. So already we have to select Fluent for battery simulation. Then these are the solvers. Then we can do the post processing in the solver itself up to some level. But if we require more post processing, or we want to transfer this data to some other post processing tool, like there is tech plot or another graphical data, so those also we can do in the CFD post. So then last we have optimization. Now in this I have one design variable study. Suppose I have multiple variable designs. I want to vary the thickness of the cooling channels. So how the thickness will affect my performance of my battery or the cooling of my battery. So that optimization I can do. So that is one. So same way I can have multiple design factor, or I want to do grid independent study. So in input Fluent battery, I am giving different input for heat generation, 5 volt, 10 volt. So with respect to when I have multiple inputs, suppose I have 550 to 100 design studies to study like this factor, but I cannot do each one by each one. So what we do, we use the OptiSlang tool, where it will create a tree and it will sense the data. So generally we do sensitive analysis, and it will predict if I'm varying particular this kind of parameter, this will have this much change in the result. So where I'm seeing the drastic more changes, more percent changes, that design I should check, and then I can optimize my design also. After that, what we do, we have Ansys customization suite. So nowadays people are working on the charging discharging part together, and we are adding our self code also. So those Python code also, or the Py scripting, we generally call it as, and because nowadays we are, earlier we used to do in C language, now engineers or the academician, they are working on the Python language. So Python language code ACT we can bring, we can generate our workflow also through ACT. Also there are some application store also, like we have Google Play Store, same way Ansys have store. From there we can bring our uh, sold examples and we can further work on that part. So for that we have ACS. Now then comes the next part. Now I have battery, I have complete battery pack which is fitted on the chassis of the car. Now with respect to fluid, I will find out the cooling part. Now if I want to see if speed, there is I'm doing fan cooling and the design is there, I want to do FSI, fluid structure interaction, then I can do in the workbench multiphysics. Same way when I'm doing uh, analysis of motor, because motor will take energy from the batteries, so how both will work together. So those physics I have to couple with, then we use workbench multiphysics. So ANSYS have this advantage where I can solve more physics together with the help of workbench multiphysics. So I'll give you some examples also in upcoming slide how we are using workbench multiphysics. So now let us come to battery simulation. So we know what is battery. Battery, either they accept or store or release the electricity based on the demand. So generally we store the energy in the battery. So there are two types of batteries. One is the primary battery and the second is the secondary battery. So primary batteries are single use which cannot be recharged, like our cells we are seeing in our AC cell, AC remote, TV remote. So we are just using them and throwing them. So we cannot recharge them. So they are cheap in cost and we can easily produce them again. Whereas secondary batteries, which are difficult to produce, and that's if you can take example of our home inverter batteries, where we are, once the electricity come, it will charge again. So this kind of battery we call it as secondary battery. Mostly in EV sectors where we have multiple application, long duration of time, we use secondary batteries. Uh, so in batteries, we have complete electrolyte level simulation. So in ANSYS, we perform from electrode level to complete powertrain vehicle system analysis. So electrode levels means we are seeing how the ions are transferring. So chemical composition. So those study we check with the ANSYS Fluent itself. There is a fuel cell model available that we study in the at the electrode level. Then we have cell level, just like today we'll cover cell level. So where we see the charging, discharging profiles, heating, how the, if I'm checking, then I can check the swelling, thermal abuse condition. So different condition we can check at the cell level also. Same condition we can check at the pack level. So what we do, we combine the cells in the series or parallel form. We create the module. When we combine these modules, we create a battery pack, and we can see the complete powertrain vehicle system integration also with the help of ANSYS Twin Builder. So there's a tool, ANSYS Twin Builder, which help us to understand complete behavior. So what we generally we do, we we solve this battery model and use the RM model to integrate with the complete Twin Builder. So there's a slide we'll show in our next webinar, and just I will give you one slide overview how we do the powertrain vehicle analysis. So you have to remember we have one active zone where the main cells will react. So we'll design this prismatic cell bed today, and we'll have two passive zones. We can call it as N tab and the P tab. N stand for negative terminal tab and P stand for positive terminal. So once we have anode and cathode, generally we denote now with N tab and P tab. So when we talk about the electrode level, we should know while designing battery what kind of battery we have to use. So based on the application we use, so there are some pros and cons, and there are different application with respect to our battery. So we know we have lead acid batteries, alkaline batteries, nickel metal hybrid materials, and lithium ion batteries. So lead acid batteries are rechargeable, extremely common, and high power density, but there are some cons. They have low energy density and very big in size. So you can see the size which are big in our home. We mostly use lead acid battery in our home inverter batteries. Then even they are not in parallel, they are single cells. So same way in automobile industries, we use mostly lithium ion batteries, whereas nickel metal hydride, they are hardly used in the our space craft, drones, portable system, like army people use when they are going to the forest area. So they are using highly current charge, so they can get more communication faster and don't have to depend on the current. So these are the conditions, so you can study about this also. Now, as a engineer, we know every academic think of that we should create a batteries EV car. Nowadays, we are seeing a lot of EV cars. So if we talk about the EV, there are four major pillars: battery and BMS. Then power electronics, where we talk about the electronics part. Then we have electric machine like motors, and then we have the propulsion system. So if we talk about the battery part, it's a main pillar of the EV car, where we study about the electrical behavior, electrochemistry behavior, thermal behavior, structure behavior, and electromagnetics coupling part also. So we'll focus on this part today. So now we'll comes to the challenges. So lithium ion battery, generally most of engineers, if you see the research paper, you will find a lot of paper on the lithium ion battery. So these lithium ion batteries or multiple batteries, you can say they are multi-scale in nature and multi-domain. Multi-scale means they can vary from size to centimeter to meter size also. So depends on the application. And multi-domain means they are not fitted only to one specific requirement. So if I have a car, it will not will not simulate with respect to particular daily location. It could go to heavy like hilly area where we require instant power, more torque power. So how with respect to that current different condition, how same battery can work and same car can transport to any cold country. So if I'm doing some battery management for Delhi, I want to make it cooler. But if I go to Kashmir or some cooling place, I have to heat up my battery. So these kind of challenges are there when battery manufacturer are thinking. So what kind of battery we should create? So that's why they classify the battery range. Okay, this battery will work up to this range. But we can manage a system in such a way that same battery can provide the cooling as well as the heating part also. Nowadays you can see AC also. So previously we used to have heater and AC separately. But nowadays, if you see there, ACs are coming which work in cold weather condition. So they have the heating coil which provide the heating heat air during cold season. Same way we have the battery which we can manage in both way. Then the thermal reliability is the major issue which comes under the battery. So how we can manage thermally? Sometimes it might not be burning, but if you see a scooty, if it is getting lot of heat, the body will heat up and it can have other thermal stresses on the structure. The life will reduce. So sometimes some design with respect to okay, it is not burning, it will not flame, but we have to see the thermal condition also, whether the person can touch sit on the part or not, because you can see when we are driving our vehicles on hilly area, the engine will get heat up. Okay, so those thermal reliability we have to maintain so that when we are passing through hilly area, the battery should not heat up within small distance. Then obviously wide ambient condition and different dry cycle. Dry cycle means how the passenger is or the rider is driving our battery. So if someone is accelerating very fast and then suddenly putting brakes, it have impact on the battery life. So the battery will suddenly charge and discharge. So these kind of different dry cycles create lot of issue in the battery. So these are the issue we are facing in the battery manufacturer thinking while designing the battery. Then safety and structural integrity and complete whole car system as a part. So for this, we don't have one single software. So if we talk about other tools, whereas in Ansys we have complete solution for all kind of these challenges. So how we cover this? We call it as multi-physics, where battery cooling and thermal part we cover with the fluid physics CFD bundle, which we have already seen. Then related to our drop test battery, then there is a impact test when the car hit. So generally car hit, it's the battery should operate and we can further move on. So those kind of we check in the structural analysis. Even when I'm putting the load on the chassis, so the load should not be that much big, the chassis should not break. So those kind of performance we check in the Ansys structure part. Then we have electronics, where we part study the motor efficiency. Now with respect to if motor efficiency is not good, it will also charge or discharge our battery effectively. So but as a starting point, we can start with the fluent part and then we can couple. So different engineers works on all physics together and they share their knowledge and do the multi-physics simulation study and complete the part. Same way if you are putting nowadays, we are saying chips or the sensor control, which will activate the cooling part only once I that battery will reach up to that condition. So those kind of we can study with the semiconductors or the small chips, the high performance chips for battery cooling, and embedded software for automation car. There we use the battery cooling part. So this is one example where I'm working on the motor analysis. And so vibration will comes in motor. So with respect to vibration analysis, I can optimize my performance of my motor, and through Maxwell we study the motor magnetic loss. All those we find. Then we'll study the thermal behavior in Ansys fluent. Now with respect to that, how much thermal stress will generate, or we can say load, due to load it will affect, and life I can predict. So life prediction of motor will also have the efficient way for the battery life also. Then these are the kind of tests we generally do for the battery simulation of when we are creating the complete EV car. So we have to check the shock vibration test, because when we are putting load on the chassis will also go in the vibration part, and during that vibration whether my battery pack will remain in contact or it will dispatch from the part. So electrical wire connection will be there, so those connection will be well fitted or not. So those things we check with the shock vibration. Then battery drop test. So during transportation it might drop, so it should not fail, the chemical should not leak out, so that drop test also we perform. Then nail penetration test, where we intentionally create, so this is like in future the car can get accident, so those kind of tests we also do. So with respect to company standards, we perform this kind of simulation. So this kind of simulation are model availables are in the Fluent, and we can see their behavior. And now this is with respect to complete model analysis. So you can see I have a driver. So this is riding the part through controller. It will transfer to the battery behavior, and it will charge and discharge. So the battery pack which we have, what we have done, we have converted our Fluent model into reduced order model. So this is like a 2D graphical representation, or we can say 1D presentation, generally just like a MATLAB. So, and we have optimized the performance. So with respect to all physics behavior of complete EV vehicles, whether it's a wind velocity or say driving cycles, I can optimize the battery pack performance. So what parameter I have to vary, so I can check in the reduced order model, and I can optimize my battery design. So this is we generally do in the Ansys digital twin builder. Now we'll comes to the cell type. So we have cylindrical cells, then we have prismatic cells and pouch cells. Pouch cells are widely used in our army industries or the defense organization for the short duration, and mostly in our home application we get the prismatic cells and the cylindrical cells. So we don't have to create the inner layers. As you can see in this, there are a lot of inner layer. There is a separator. Then we create in Fluent. What we do, we simply create a domain complete and we'll simulate. So we'll provide some internal heat source, and through that heat source, it will provide the heat. That is normal conjugate heat transfer method. But if I'm going with the electrolyte level, so even there also I don't have to provide this kind of internal details. The reaction will take care of that inside physics behavior. So we have to activate those equation, and automatically it will take. So we have to provide the outer part, that is our size and length of the cells. So there are a lot of batteries, not only EVs, aerospace and defense, then transportation. You can see metros, trains are there, and then consumer electronics in our mechanical when we are working in the some plant layout. So we used to transport with the diesel vehicles. Now all those already transferred to the battery vehicles. Then healthcare system, oil and gas. So in healthcare system we have ventilator, so they operate on the batteries. So with respect to the battery, how it going to be used, we can design and we can study that surrounding condition, what will the temperature, if it is operating in higher ambient condition, so what could be, how I can develop, so what could be the maximum temperature. Then home appliance with respect to power, because heat generation is directly lead to the power generation, so how much heat we can control. And in data centers nowadays we are seeing India is going towards the more creating more data centers, so we require more battery backup. So battery sector is also indirectly is coming for major requirement. So as we are talking about the heat generation, so when we are discussing with the battery, there are two things plays very important role, that is C rate. So C rate is generally we call it as state of charge. So how my battery is efficient charging, how speed it will charge. So we have C rating like 0.5 C. Suppose I have battery, we call it as 1C. So it will complete discharge within 1 hour. So I will have 1C rate. If it is taking more time, discharge time is 2 hours, I will call it as 0.5 C. 2C 30 minutes, 5C 12 minutes. So more we go towards the 2C 5C, it is means it is fast charging. Nowadays what we required our mobile to charge within seconds, minutes. So what we have fast charger. But in fast charging what we require more power. That means it will generate more heat. So those comparison we can study and we can identify with respect to the ambient condition how much heat it will generate. Okay, and whether which C rating will give us better efficiency. Through graph study also we can optimize our C rating behavior. So generally when we talk about the battery thermal simulation, we study the C rating behavior as a basic level. Then with respect to our further requirement, we can study further input also. So if you have already worked on the Fluent part, you might have seen this windows where we have different models, multi-phase model, energy model, viscous model. So same way we have the battery model. So once we activate this battery model, we have further solution method. So we have CST coupling, FMU CST coupling. So with respect to the requirement, how the industries are working, we study this behavior. So our major focus remain on the thermal analysis of batteries. Okay, so we find out heat generation rate or the couple thermal equation, how we are solving and how this behave. We have four methods. So in CST is the first method where we directly give the voltage. So you might have seen some information will be always available on the battery, whether it's single how much voltage is there. So when we have this kind of input, we can go with the CST. So CST have advantage. So we don't spend that much time. We can simply give the voltage and we can perform the steady state analysis. Okay. Then we have FMU CST coupling method where the industry have the data and we have to take the data and we have to with respect to that data we have to simulate our battery. Then we have circuit network method. So if we activate this circuit network method, our e-chemistry model will solved, whereas in CST method our e-chemistry model will not be solved. So the e-chemistry equation are not solving, but we are getting a tentative idea how this will behave. Whereas if when I enable this circuit network, so this is more related to electrical network diagram. So we have studied resistance, capacitance, how we creating the complete network behavior. Same way when we are working on the battery pack, we generally use circuit network method. And in last, when we have kind of lithium ion batteries, we generally use MSMD model. So MSMD model gives more better accuracy as compared to circuit network model or CST coupling method. So when I enable this MSMD model, you can see there are four models. So these are the three scientists who have developed the equation and validated the results, and Ansys have developed those equation and validate with the simulation also. So ECM is like we can say it is physics detail is very low. So this is like when we don't focus more on the physics details, we can go with the ECM models. And whereas I want to work more on the more physics detailed behavior, then I can go with the Newman PT2 model. Whereas if I'm looking for medium kind of physics of the chemistry behavior, then I can go with the NTGK. So most of researchers they prefer this NTGK model because it take less time and it is in the range of accuracy also. So it will give accuracy near about that part without wasting that much computational time. Then if you have a Euler defined model, you can use the Euler defined model also. So in ECM model, it will run very fast and we can pack very easily. So the packing, when we have a lot of cells in battery pack, we can easily solve with the help of ECM model. And there is also thermal coupling we can do in the ECM model. Then if we talk about the NTGK Newman model, so it is highly chemistry is involved. We have to consider the simulation time will take more time because if we are solving our chemistry behavior more realistic, so more number of equation will be solved in the background and we can complete solve full chemistry behind. So someone who are working on the more chemistry behavior of the cells want to study more ionization properties or the how the inside the cells are reacting, chemicals are reacting. So those things we can study in the with the help of Newman PT2 model. So coupling is somewhat limited in this Newman PT2 model with the thermal part. Whereas if we talk about the MSMD, it is well advanced. Okay. So I will show you this part. We'll go with the CST coupling also and MSMD model also. we can do modeling of the batteries. You can see in the slides. So these are Ansys images where researchers have created the battery single cells and created a module. So what we have one pack. So this is my one complete pack. So each pack consists of 12 modules. So in this stage, 12 cells, and we have done polyhedra mesh. Okay, so this is one module, and these modules are combined and it will forming a battery pack. So we can go up to more. So in the size they have taken around 4.3 million in the mesh count, and you can see the mesh. This is fluent meshing they have done, and this is also fluent meshing. So they are connecting the tabs to create the form of series and parallel connection. When same tabs are connected, we call it as parallel connection. When positive and negative connect, we call it as series connection. Then we can find out the heat transfer rate, how the battery will generate the heat. So heat temperature contour we can get it, or the magnitude also of the current, also how current is flowing across the cells. So that gives us idea to the electrical engineer also. Then, like with respect to single cells, we can identify the voltage difference with respect to degree of discharge, whether it's a cylindrical cells or the prismatic cell, and we can identify the current flow direction also, which gives us better idea. And the major, what as a thermal engineer, what we study the temperature behavior. From temperature behavior, as a mechanical engineer, we identify the part. Whereas the voltage is also very critical, up to which voltage, because we have to maintain that voltage. If the voltage drop below that or exceed that part, it is very danger for the battery design also. So that's why we monitor the voltage plot also. Then we can pack. So we'll study this packing also, how we can do the packing and unpacking. So whether it's a single series or big series packing. So these are few examples, like when we can do the battery pack, and we can see the battery cooling. So for that we have the cooling channels through which CFD play very important role to identify the path of the flow, how we should flow the part. Now let us take with the hands-on. So what we'll do, I will create a model of the prismatic cells first. So we have to open the workbench. So what we have to do, we have to open the, so workbench, as we have mentioned, it's a platform where I can solve different physics, like fluid is there, fluid flow, then structure physics is also there. And even in the same physics, I have CFX is there, polyflow is there. Like if I'm working on the uh, fence pies, I have to couple with the fluent part. So same physics also we can couple. That's how workbench give us the chance to couple our physics together. First we'll save the project, save as. So it is good way to save your project, because when we are not saving project, generally what happens, it will save in the C drive by default directory, the installation folder directory. But if we save at our location, we can have better control of our output files. So we can study if sometime project corrupts, we can recover some files from that particular location. Whereas in C drive, it will go to temporary folder files. So I'm saving in the new folder. I'll name it as webinar, and I can save it as a single cell. Prismatic. The extension will be WPPJ. So okay. So sometimes what we do, student they share only WPPJ file, KB file. It will create a shortcut only. But if you have to share the complete model, you have to go to file and archive the project file. So it will complete your complete file. So instead of copying folder and folder, you can go to the archive part. So I will show you in the last how you can archive the project. So as of now, we have two options. I can go with the fluid flow fluent meshing if I want to do the fluent meshing, or I can go with the workbench meshing. So for workbench meshing, we take the fluid flow fluent. So one problem I will showcase with the workbench meshing, and other cylindrical I will showcase with the fluent meshing also. So we'll create the model. So for modeling, if you right click on this part, we have three tools: space claim, discovery, and design modeler. So I'll do the modeling part in space claim. Now to create any drawing, like first what we do create a 2D design, then we'll add the volume to that part. It will go to 3D model. So for 3D part, we have the design tab. For 2D, we have the sketch tab. But to select our plane, we have to first go to the design tab and click on the 3D mode. Then go to sketch mode. To select any plane, I can move my mouse and I can select any plane with respect to my requirement. Or there is a direct rule, whatever the plane you require. Like I want to take XY plane, I can directly click on the Z axis. So it will select only perpendicular plane. So if I want to select YZ plane, I can click on the X axis. So as of now, we'll take XY plane. So I will click on Z axis. Then we can press I button or V key for the front view. So front view, whenever we're creating design, it is always recommended to go in the front view because it will reduce our human error in the designing phase. So now I'll take a rectangle. So let me tell you what I'm creating. So you have seen this prismatic cell. So I will create this kind of similar design with random values. Okay. So I'm taking a rectangle. So you can start a defined rectangle from center, or you can directly create a rectangle from one point to the another point. When we take rectangle from center, I can take the center point and I can create like this. Suppose this is 220 and 350. So length I have given 350 mm and width I have given 220 mm. Now this is, we will end the sketch. We have to create part by part one so that I can define my battery component. So I'm creating a component cell. First I created the sketch. Now we'll go to isometric view by pressing H key. And then I will give thickness of my cell, that is 10 mm. Now this is my cell. So I will name it as, I will go and right click, move to new component. So I will name it as cell. And then we have to create the tabs. So I can select the top face and go to sketch mode. Front view, Z key. Now select the rectangle. So I have option, I can create both tab together also, or I can create separate also. So if you want to create together, you can use this line, center line, and set as a mirror line. Okay. So I'm passing the time. I'm just creating both together. So you can select the distance. Or I'm giving, you can press tab key to alternate the dimension. So you can see now it is highlighted in the length direction. If I press tab key, it will highlight in the width direction. So this width could be same or it could be different. So depends on the size. So as of now, I'm considering same dimension. Okay. I'm giving 42 mm. Now this should be some distance from this. So that's distance also we can specify with the help of dimension tab. Select this first point and the distance. Suppose this is my 20 mm distance. Okay. Or you can give 30 mm also. And this will be, we have given 42. Clear? So like this way, I can control my design with respect to my previous reference. So that's why we selected that plane as my reference plane. Now end the sketching. Go to isometric view. Select the face. And we can pull 40 mm height. So it is my P tab. So I can name it as, move to new component, P tab. So, and I'll select this face and give same height 40 mm and name it as N tab. Okay. So now if you see here, I have separate assembly and separate components in a complete assembly, design one assembly. At this location, the upper tab lower surface and the cell upper surface, there is a overlapping. There are two surfaces. So we don't want to have this kind of things when we have a complete assembly. If it is a single design, that it will be taken care. But if when it is separate component, we should have one common surface. So what we do for that creating node to node connection, we use the share topology. So you have to go to workbench inside the space claim and use the share topology. So it will highlight the common interface surfaces. Okay. Now click on green tick. Done. Now we have option to give naming here in the groups in the space claim. So naming is very important when we are solving any CFD problem. Okay, even we are solving any FA problem. So it will help us to identify what are the parts, and same way, since I have given the assembly name, it will be identified by the solver. But if I have not defined the name here, it is not understood by the fluent solver. So we have to give naming. So I will give the naming in the meshing part. So modeling part is done. So you want to copy this, you can simply select this, and you can go to move command, design, move, and press control key while moving. So it will copy paste. So like this, I can create the battery pack multiple times, but as of now, we don't require in our current case. Okay. Then we'll go to the meshing part. Sorry. So we'll go. So these are the cells. So generally, we have seen observe like a lot of times students are working. They are creating the model in the Fluent. So what generally when I take workbench in the fluid flow Fluent, what the Fluent solver understand that this is a fluid domain, but in actually batteries are solid in nature. So we have to define them as a solid. So they have taken solid, but sometimes it is not detected by the solver. So we have to convert this solid to complete solid. So this step is required. Solid. Sometime even if you miss, you still can change in the Fluent by going to the cell zone condition. So there is another option we have. Now we'll generate the rough mesh. This is the units are in meter. So I can change the units from the top, mm. So default is 22. So you can see what we have. We have the structured mesh. So this is structured mesh, but there is a one node. Okay, one element only. So as per basic principle of element, we should have three element across any minimum thickness. So we'll reduce the size. So let us take 1 mm and see the part. Now you can see we have very good structured mesh, and mesh is also fine. Since this is design very like simple design, we can say all rectangle parts are there. But if we are doing battery cooling, so there might be some curvature part. If we have cylindrical cells, so there will be unstructured mesh. So those mesh we also can convert by using mesh method also, with the help of multi-zone method or other extra dominant method. So as of now, the mesh look good. We can identify check also with the quality. So in meshing, we check the mesh matrix. Orthogonal quality, we check for the CFD and the skewness. So orthogonal quality should be near to 1, and minimum should be 0.2. So most of element we are getting one value, minimum also maximum in that part. So same way we can check for the skewness, and skewness should be maximum 0.8. So now here we are getting skewness near to 0 only. So the quality of mesh is good. So we can go ahead with the naming. So I'm just hiding this graph. Now naming is important. So so in the mesh window, you can see there are 4 tabs. Okay, body, then to select the body, then to select the face, to select the edge, and to select the vertex. So when I'm doing CFD 3D simulation, we prefer body selection. Okay, so we'll select the body, and there is a shortcut. You can press N to create the name. So this is my cell, that is active zone. Then if you see the P tab, you can highlight and cross verify. This is my P tab. So you can select this body again, name it as P tab. So I'm naming it with small name, and select this, name it as N tab. Now this is we know our battery, how the current will flow when it will be connected to some external part. So we should have to create connector also. So P tab will be connected with P terminals, and N tab will be connected with the N terminal. So we have to select the surface. So we are not creating that design wiring design. Okay, so what simply we design in our battery simulation, we select the top surface and name it as terminal. So this is my P terminal. So I'm pressing N key and name it as P terminal. These terminals and tabs are very important when we are using MSMD model or using battery model. This is my N terminal. Because if we will not give this kind of naming terminals and tabs, we will not able to select the battery connection in the battery model. Now we have provided the naming. You can cross verify cell, P tab, N tab, P terminal, and N terminal. So I'm keeping press control key and selecting all names. So you can display also like this. Now we'll transfer this mathematical model to our Ansys Fluent. So we will update it. Then you can see a pop-up window will come and it will define that mesh translation to Fluent was successful. So our modeling and meshing part is complete. Now we'll go to the setup part. So setup is like this is launcher. So we have 3D model. So that's why you can see it is already highlighted and we cannot change it. So then double precision for higher accuracy. When we are simulating our equation, every time it should solve the equation precisely. So we have to always check double precision, and processor we can go up to 4 number of cores. So depending on the license you have, we have to select the number of cores. So this is here. You can check your number of cores in the task manager. So you can right click on the bottom task manager and see the perform CPU. In CPU you can see the number of cores. So I have 10 cores, but still I have the commercial license. I can go up to 4 core only. If you have the teaching license, you can use maximum 4 cores. Whereas when you're working on the research part, you should have research license and you can go up to 16 number of cores. Okay. And the hardware should also have same number of cores. Now click on start. So if your research problem is very bigger and you require more number of cores, then you can go with the HPC license also that comes along after the research license, not with the teaching license. So we have to see our projection also how we are going to use our for research part. Now we click OK. So first I will go with the CHT method. Okay, I will show you the difference how we are getting the if without solving like chemistry, physics, chemistry, how we'll get the value. So you can see this is general purpose tool. So this is like our task. If I'm solving incompressible flow, I will go with the pressure based. If I'm solving the uh, compressible flow, I will go with the density based also. So this we cover already in the CFD webinar. So as of now, we don't require as we are not doing any cooling part. So we have to see the time point of view. So whether you are simulating a battery with respect to time or you want to see final solution. So when we are looking for the final solution, we go with the steady state simulation, which is not dependent on the time. Whereas when we go with the rating and we want to see the temperature change with respect to time, in that case we go with the transient case. So as of now I will go with CHT method, so I don't require transient. I can directly go with the steady state and I can see the final temperature. So we'll go with the battery model first. Enable battery model. Okay, now I will go with the CHT coupling, that is first method. So you can see CHT coupling. So if I go with MSAMD model, then these models will be activated like circuit network. These models will be activated and you can define the C rating. Okay, then the C rating is the charging rate. So when we have to stop our simulation, when this voltage condition will come. So when we are going with higher C rating, this voltage will condition will come very fast. So in that condition, what we create is like the state of charge condition, because battery never get completely discharged. So we'll keep that condition. Okay, so with respect to multiple condition, we have different part. As of now, we'll select the CHT coupling method and we'll enable the heat joule so that we can identify the in the temperature in the part. Now we have active component, that is my cell. So we'll select the cell. Since we have given the small alphabet names, so these components will come as with names. So passive component, N tab and P tab. So in this cell, the reaction will take place, but in actually we are not giving reaction. We are just defining the battery model. Then on these tabs, this is my passive zones. So when you have complete battery pack, other things, the which where the reaction are not taking place, we have to keep in the passive zones. Now we have the external connector, that is negative terminal will be N terminal and positive terminal with P terminal. In case when we have a lot of battery specs, so there if I go with the modeling part of complete terminals and the connectors, it will take a lot of time to create model and meshing also. So generally there is another waveform we use, virtual battery connection, for the virtual connection to reduce our computation time also. Once, as of now we have single cell, so we don't require. Once you provide this input like active passive zones and contacts, we have to click on the battery connection information to cross verify whether my battery model is right or wrong. If your namings or the connection are wrong, it will throw the error. Suppose if I take here also end terminal and click print battery information, so you can see it will throw the warning. Okay. Even if I don't select proper zones like here cells, then again I click on the battery information, it will throw the error. So this the advantage of Ansys Fluent battery model. It will throw up before simulating the run. So we can again identify and we can save our time also. So for positive tab, we'll select the P terminal and then we check the connection information. Same way with the series connection and parallel connection. So we might see the connection also, whether my connection is right or not. That also it will display the complete battery connection information. Now we have model parameter. So here I can give some 10, 20 voltage, or we can take some generic with respect to our part. Suppose we are taking 10 volt. Then current, in CST method, we are not solving current. Okay. Whereas when we go with the electrolyte level, we have to solve our current value also. But as of now, we can give some default value for 10 ampere or 100 ampere. It will not have that much effect. Simply the main heat general source is cell 10 volt. Then we have to apply. Okay. Then if you're using some import UDF function for your particular parameter for battery different model, this will be activated with respect to option. Then you can see year wise there are a lot of battery models are enabled, like battery swelling model came, then complete pack builder came. I want to reduce, like we have seen complete EV train vehicles. So we want to analyze the complete EV vehicle behavior. Then we can convert our battery model into reduce order model. Then gas venting problems, whether the gas will leak or not, that we can identify with the battery venting model. Then we have thermal levy. So all these things will cover in the upcoming webinars. So stay connected with us. So now, as of now, for today's case, we use direct voltage, apply, and OK. Now next part is very important, that is material. So in battery, what we have electrochemistry, we take it as a electrolyte material. Okay. And that will be, we name it as E material, or you can name it as another kind of whatever the material name you want to give. But if you provide E material, it will have better part. Now I am just changing the material, E material. Chemical formula we don't know, we can keep it left, or if we know, we can simply keep E. So here I'm giving the density of my electrolyte material, that is 2092. So I'm referring from one paper. Okay. 678. Specific heat, thermal conductivity 18.2, and electrical conductivity. So this is like, if you have worked on the CFD earlier, you might have seen we are doing initialization and we are activating the part. So initialization we are selecting. So in batteries, these electrical conductivities are our major parameters to start our equation. Okay. So we will use them as defined per UDS. So in CST method, we don't require, but still we can give 1.9 e to power 6 power 6. Okay. Now it will ask whether you want to remove the material aluminum or not. So if you require that aluminum material to tabs, we can keep no. If you don't require, you can click no. Okay. If we require, we have to click no. If we don't require, we have to click on yes. So as of now, I required aluminum for my tabs. So I'll click no. So it will have both materials. So now you can check inside the solids. We have E material and aluminum. So now tabs can have the same material, or we can have the different material also. As of now, I am taking same only. If you want to have another material, you can again go to this Fluent database. So this is the material which I have created, e-material, which is not available inside the our Fluent library. But if we have a lot of time, we have the fluid material available inside our Fluent library, so that we can select from the Fluent database. We can select the type of material. So it is a solid. So I can select solid, and then I can select the part copper. Suppose I want to select the copper, so I can select copper, copy, close. Now close. So now next part, we have added the material to the solver, but we have not assigned. Now our next task is to assign the material. So that will give in the cell zone condition. So you can double click on the cell zone condition. The task page will open on the right hand side. So cell where the reaction will take place. So we'll select the E material. So we'll change from aluminum to E material. Apply, close, then end tab. If it is aluminum, we'll keep aluminum. If you want to change to copper, can change to copper also. As of now, we are not changing. I will keep both aluminum only. So, but if you want to change, you can change also. Okay. Now we'll go to boundary condition. So in CFD, if you worked previously, there you will see there is lot of inlet condition, outlet condition. So when we do battery cooling, we have to provide those inlet condition. But as of now, battery, what we have to provide? We have to provide the ambient condition. What will be the ambient condition and how the heat will transfer from this battery to the ambient environment. So those we have to give the convection value here. So we can go to whole cell convection. Suppose my convection to the ambient temperature is 5. And this is, you can see the tab free steam temperature. This is our ambient temperature. Now it is showing the Kelvin around 26. 300 Kelvin. I can change to units and change this value to the degree Celsius also. So we can go to the units. Any units you want to change, we can change by selecting the units, and we can simply select the unit we require. If it is not there, then we can create a new and we can decide the factor and we can provide that value also. Most of units are available, but in case it is not available, we can create our new units and we can decide the factor also. Now you can see it is converted to degree Celsius. Suppose my ambient temperature is 35. Okay, that is generally we get in current condition. Now apply, close. Same way we have to see whether I want to transfer heat from the taps walls or not. Then I can select the part convection 5. But we have to maintain same temperature for each case. It should not be different. The free stream temperature, that is ambient temperature, should be same for all my boundary condition. Okay. So this is like important. So generally, if you are having heat flux 0, suppose there is a complete heat source like heat sink we provide heat flux. When we have adiabatic condition, what we keep heat flux as value 0. Then if you're providing constant temperature, like you're putting some burner, in that case, we provide the temperature value at that particular temperature we want to maintain. Then convection, our normal natural convection, if radiation, like through solar radiation emission is there, we enable the radiation. If there is a both convection and radiation, then we'll select the mixed part. So in our current case, we are doing the heat transfer through from the battery to the ambient environment through convection. So we are selecting the convection part. For conduction, what generally do we need the steady state thermal. Okay. Now we'll go with the next part. So I have just giving initial value, and now next part is controls. So I don't have any fluid here. So I don't want to solve my fluid equation. So what I can do, I can simply go to equation and turn off my fluid equation. Okay, when I do battery cooling, then at that time I require those conditions. As of now, I require only energy equation and the battery equation, that is UDS equation we have given in the material part. Okay, then I will initialize. Initialization means as of now what I have given initial condition, and I have to give value to each cell center, because in CFD we solve with the finite volume method, and at the initial stage we have given at the boundaries only, but I want to have at each cell some value so that I can start my calculation. So that we do in the initialization. Standard means when I take from particular some value. Okay, hybrid, it will take the average value of all my boundary conditions. So we'll go with the hybrid as of now. And then we'll go to run calculation. Suppose I'm giving some here 100 iteration just to showcase you the value with respect to 100. So my ambient temperature is 35 degree and the voltage I have 10 volt. Okay, with respect to this design, how much temperature it will generate, that I will check. So most of time a student also feel same thing, like you can see battery they simulate very fast and they go with the maximum residual. So within 4 iteration it is showing converse. So what we have to do in such condition, we have to go with the uh, monitor part and residuals. Okay, so now we have to decide the converse criteria. So generally we can go up to e to power 17 or e to power 18 so that it keep converging. So or another option what we have, we can go to the advanced option. We can reduce this criteria condition and the number of iteration we have given, it will solve up to that number of iterations. Same way in the transient case, when we give any input with respect to that time, it will solve up to that time. So mostly in battery case, you will see the residual will come very down very fast and your simulation will stop. So you might feel that my simulation is converged. No, but you have to run further properly until you see a graph constant. Okay, so I will again initialize since I made the changes on the top side. Initialize. Okay, now I will run it. So I will run for 100 iteration. So now you can see after 10 iteration, the graph will became constant and our result is to it power 18. But we'll still further run over 50 iteration. So in the meantime, when the run is going on, I will cover some slides. Okay. So this is the metal properties we have taken. So when we go with the transient case, we will define both UDs. So this is the potential difference generally create between the batteries and start our transient case. So this is one case study. So we can simulate our like most of we do the cooling part and widely industries are using plates for cooling purpose. And then we can compare the temperature with respect to time. So for this time study, what we generally do, we go with the transient case as you have seen. And for battery cooling, we can provide inlet and outlet. So this is you can see if I'm passing some fluid from here, it is cool. But when it is coming to outlet, it is taking away heat from the batteries and it is coming at the higher temperature. And they have validated also with measurement with the practical and the simulation. And these are well matching. If it is not matching, still you can see the graph should follow the same pattern. Sometimes it is not compulsory, it will completely match because our result depends on the meshing. Okay, how we are doing the meshing. If we change the mesh will also change. So for that we do grid independent study, but the pattern it should give in the same way. How if it is the sudden spike, it we should also get the sudden spike. Then we have part. So for learning path, what we can learn from the basic concept path that we have Ansys innovation course. So you can Google it, Ansys innovation course. You will get the courses on the path where you can learn basic physics of any physics like mechanical structure, thermal, vibration in CFD, turbo machinery part, then fluent part, battery is course. There are few courses, but more is on the NC's learning part, NC's learning hub. Then we have some queries you can put on the learning forum as well as you can reach out to us also. And if you require some certification, you can go for the certification. So the certification are in the two forms. One is the batch when you complete one module, one small course. When you have 5 to 6 course in one certification, you will get the certification. So certification are charges based. So if you compare from last many years, we can see one by one sport was there. Then there was some content came, then learning forum came where we used to ask question. So this was up to 2014 to 2022. But if now we see today's scenario, you don't require any that much big trainer. You have the AIC courses where you can learn basic fundamentals, and we have the Ansys GPT also. So just like we have GPT, so we have Ansys GPT for the users who are actively in the ACS, like under maintenance part. So you can directly, when you're doing simulation, you can simply ask the question and it will guide you what is the next step you can do, and what kind of courses theory you want to learn, or how the equation are running in the background. So these are the courses available on AIC courses. So these are mostly with respect to electronic physics to understand the for the electrical part, whereas for the CFD part also there is a courses on the Ansys help menu section. So I'll just show you current case which I have taken. So you can go to Chrome for the your browser, then directly type Ansys public version help. Okay, so once you click on this Ansys public version help, we'll get to the Ansys page help, where you can see the complete tool are there. So as of now, we are working in the Fluent tool. So you can go to D2F, click on the Fluent. You can select your version. So it is having data from 24R2 to 26R1. So you can see the latest version we have 26R1, and you have complete theory guide, user guides. Okay. And there is a complete tutorials. Then we have the complete videos related to that part. So if you go to tutorials, you can start with the first part so that you can get the user interface idea, how the Fluent is there. Okay. And then we have the battery model here. You can see the simulating single battery cells and then battery pack. So same battery we have taken, but I have done with the help of modeling and meshing. They have provided the mesh file. Okay, so you can download these files. These are easily available to download. You can simply click on download and you will be able to download the mesh file, and then you can follow step by step. So this is, we have Ansys help where we follow with the help of PDF. Now, if you want to have some lecture, you want to go with the lecture part, what you can do, you can go with the Ansys innovation course. So this is learning platform where this is basically for students and the professor when they are at home or they want to learn something. You can select the free courses, or courses are there. You can select the filter. If you want to learn CFD, you can go with the fluid physics. If you want to learn the FEA part, you can go with the structure. So there are around 274 courses in the fluid itself. Click on fluids, filter results. So you will see the courses. So these, if you complete these courses, you will get the batch. Whereas if you want to have multiple courses, then you can go with the part. So I'll just show you a simple example. So calculation is complete. Just give me 1 minute. I'll complete this. So this is fluids. Okay. So if you go to this course, you can, it will take around 4 to 6 hours. Now on the starting, we have the theory part. Okay, so you can understand the basic concept, what is fluid, how, what are the properties of fluid flow classification. Then we have 4 example also of simulation. So, okay, so this is where help a student to learn the simulation part also. So in example, these are viscometer. Then we have natural convection square cavity. So these kind of examples are there. So if you go to these courses, there is a complete file they also provided, like mesh file they have given. Okay, and you can get the video also from the YouTube. So complete step by step. So instead of doing with the PDF, if you want to go with the video, you can go with the Ansys innovation course also. And there's a case and data file also to compare your result, because sometimes what we do when we are doing, we face a lot of issue, we might not get same results, so that we can compare with the case and data file also there. Then next comes, we have Ansys learning hub. So this is like subscription base. We have Amazon Prime account or Netflix account. Same way for the students, we have the Ansys, not for students, for faculties or the researchers. We have Ansys Learning Hub, where we have advanced problem on the battery simulation. So you have to take subscription. So it's a charge, yearly based charging. Then what is the advantage you have? You can learn any physics here, not only CFD, any physics here in the advanced way. So more research problem, more industrial case studies are there, which you can refer and you can learn the part. So I will just show you some fluid part, CFD physics. So this is the campus. Generally, we call it as campus. Every college have this map. So this department is the dead side. Same way we have the Ansys camp. So if you want to learn fluid physics, you can go to fluid. If you want to learn automation, you can go to the automation part. Optics related to light simulation or camera sensor simulation. I will go to fluids part. Now here you can see with respect to your basic to the part. If you go to the basic part, it will take you to again to the Ansys innovation course. So AIC have only in this much domain. But if you want to go with the more further part, there is lot of modules. So this is with respect to they have the PDF files and the file also. So if you want to learn CFX and other fluid products, so there are new products came like Rocky came, Free Flow is there, which is mesh like technique more advanced nowadays, like for open channel flows. Then we have Polyflow, Forte. So with respect to your tool requirement or a physics requirement, we can directly go and we can simply search also in the top part. Suppose I want to search battery. So it will give me all courses related to the battery, whether it's a mechanical domain or electrical domain. So you can filter out this part and you can understand the part. So I will just open you one case. So a reduce order model, I will show you. This is slide. So like this, you will get the PPT, just like PDF. And to run this setup, what you will have in the next part, you will have the file. Okay. So this is file zip folder where you have the PDF file also, the PPT and the case and data file also for the comparison study and the mesh file to run your setup. So this way you can learn where you don't require an instructor. Also, there are online courses also here, e-learning we generally call it as, which you can refer. Okay. So you can go to home page. And there is a enroll classes, like you will get the calendar also, and you can get the complete part chart also, whether you have completed that course or not, or whether it is in progress. So this will give us better learning experience, and we'll get more content, more research topic. Okay, so this I was talking about the battery calendering part, manufacturing. So this is with the help of Rocky tool. So you can see calendering. I will just give you some idea. So once you're complete, you can retake the session also. So you can just go to previous page. So this is optics length sensitivity analysis they have also performed. So for this, they have given complete simulation. Okay, uniform. So the calendering part and we do with the help of Rocky. So this is the Rocky physics they are working. Okay, same way when we are working with the e-chemistry behavior, we go with the fuel cell model. So there is a in battery potential electrochemistry fuel model. So you can go in the theory part also with the potential model. As of now, so this is you can get the experience of the Ansys Learning Hub. So this is are the learning resource we have. We have YouTube channel of Ansys also where you can learn the basic physics of CFD part. Now we'll come to our problem statement. Now we are run it. We'll check the temperature for current case. So we have to go to results, graphics, contours, change to temperature, and we can select the volts, save and display. So now you can see. So this is we have given 35-degree ambient temperature with respect to 10 voltage. We are getting around 45-degree temperature minimum at the taps and the maximum 47-degree. So you can see here we are getting proper heat transfer. Okay, in the cells. If we get somewhere high spot and somewhere very low temperature, that means the heat is not transferring properly. We have not analyzed properly. So same way we can check the other parameters of batteries, contour, temperature, then they are battery variables. So we can see the potential field, but these comes when we enable our uh, M these models, other models, MCM model. In CHT, we just get the idea and we can run it more faster way. So let us go with the our MSMD model. So again, we have to go to MSMD models. We can go to MSMD. We can select NTGK model. Here I can define the C rating. Okay. Suppose I'm going with the 1C rate. Then we'll go to, I don't have to change my conductive zones. Contacts are same. Parameters are so this is reference capacity, this is the cell capacity. Okay, so you can provide this value also. So as of now we are keeping default, but if you have some cell capacity like 6 ampere h, 10 ampere h, we have to define that. So in actually how much it is there. Okay, so now okay, click OK. And for this what we have to do, if I want to see with respect to time, I have to go with the transient case. So I'll change to transient. Then materials, we have to provide that electric conductivity. Solids, E material, defined per UDS. So now this is 9.83 e to power 6.5. Okay, change and create. So now we have assigned in the cell zone condition, we don't require. So what we can do, we can add some graph here to monitor our progress while with respect to running. Okay, so those things we do in under the report generation. So we can measure the voltage. So we'll go to report definition. New. So we can create a surface report, area weighted average, and we'll name it as voltage. Voltage VP. Then we can select the variable instead of pressure. So generally when we solve CFD flow pi type, we select pressure and velocity. Here we have to select the battery variables because potential is the battery variable part. So this is passage on potential and we'll select at the tab P. Okay. So if you want to see with respect to rating, it will once I create a report definition here, you can see voltage P, it will generate a report plot like this. Here, this is plot file it will create. If you want to change the name here, you can name it as plot title with 1C rating also. Okay, so this will give us idea. I'm plotting this with what name. So as of or if you want to change here file name to save in the background and to compare later on, you can give the name here 1C. 1C. So like this, I will create multiple file. I will run and I will then in the last I can compare 1C and 2C rating as well as with the 0.5C rating. So I'm just showing you how we have to change. Then same way we can create another report. If you want to create like volume report for the temperature, report definition, new volume report, temperature, that will take maximum temperature. So out of these cells where we are getting the maximum temperature, I can name it as maximum temperature. Okay. Okay. So there are multiple options we can go with that part. Now we'll create two parts. We can go with the initialization, hybrid, initialize. Now we'll run it. So I'm taking big time step here. So this is transient case where if I multiply this time step size into time, that will be total time. Suppose if I'm taking 100 and time step size I'm taking 30. So sorry, 30. So if I multiply with this, it will be give us my total time. But generally, when we have high C rating, we don't go with that much big time step size. And for good time step size, we require good mesh also. So I'll just click on calculate. Now I can see the variation of temperature with respect to the time. Okay. Okay. Just a second. Just a second. Why it is not writing? Give me a second. You want to stop like sometime what happens, you select some function and it is not working, so you can stop it here at the I have stopped at the end of the time step, so it will complete one 20 iteration, then it will stop. Okay. So here, like now you can see voltage. So this is our plot of potential discharge uh, curve at 1C. Now it is seeing here. Uh, So I can further continue with the run. Same way we'll get the maximum temperature plot with respect to time. So initial, we have given the initial state like it has taken 26 degree part. So with ambient temperature, it will rise. With few iteration, it will go to that condition. Default condition is 26. Then I can see the complete rise in temperature. So the temperature we got 40, that it will take some time to reach that condition. And we don't know like because we have given different voltage. If we calculate voltage with respect to C rate, then we might get similar kind of temperature. Same way, I'll show you the cylindrical part while the run is going on. Okay. So if any question, you can ask me. Can we make electrical connection in this model? Yeah, we have made the connection. Their part, that connection are taken care by the model itself, battery model. So as of now, we have activated the MSMD model. So the background electrical connection are taken care by the our battery model simulation. Okay, so physics and chemistry. So for physics and chemistry, for chemistry behavior, we have fuel cell model. So if you go with above the potential electrochemistry model, you can check this fuel cell model. So you can decide with that part. So manufacturer, they are doing with the process of the manufacturing in the potential electrochemistry behavior. But as a simulation engineer, we should know what is the thermal range will come, how much voltage will drop, okay, how there is a discharge curve. So those inputs we can identify. And when you go to battery models, we can have multiple options to go that part. Yeah, these courses are free of cost, but the certification will charge you money. Can we simulate water content having two plates of terminal cathode and anode? Want to check bubble formation? Contain, yeah. Not only battery model we have to use in this. When we have the bubble water also, then battery model we have to go with the potential electrochemistry because we are working at the electrochemistry behavior. You have to use potential electrochemistry model. So you can check in the theory background of the potential electrochemistry model. You can go to the research paper website. There are some case studies also you can refer. So I will try to share with you, Prashant. Uh, Even if you Google the Ansys ResearchGate. So just let me search gate or research paper on battery using Ansys. You can simply start with this part. Okay. So there are some case study will come. Okay, analysis of battery pack with using Ansys. So you'll get the free paper also like this. Simply you have to just type battery with the battery using Ansys. So we'll get some paper and complete details of those part. These are done by the Ansys like scientists or the researcher who have used Ansys tool. So there are a lot of case studies, meshing also view. Okay, and they have given the step also. You can see this complete. They have given the tool guide. Any other question you have? Okay. So in the meantime, I'll show you the second part. It is single cell. So we have done at multiple case. Okay. So when we go with the transient, we can go with the complete. We can import the mesh file and we can do in the post processing in the CFD post. That is result part. Okay. So I'll just show you these results. So I'm closing this part. I will take another 5 minutes. Then we can wind up. Okay. So this is I have cylindrical cells. So I will just show you the model also once it is closed. Okay. This is my cylindrical model. So I've taken a cell, a lithium ion 1865. 18 denotes the diameter of the cell. and height like 65 denotes the length of the cell. I'll just show you the model and the mesh view. So you can see I use shear topology. So I have defined the cell zone and the tap zones. So in cells, you can measure tool. So this is my diameter 18 mm. And if you want to compare the length, you can select both and it is 65 mm. Okay, then I have provided the names. You can see the namings, cell wall, tab negative. So in cells, cylindrical cells where we have the negative tab at the downside, then tab positive on the top. So this is a terminals only, okay. And the terminals we have given, we have named it as here, and the complete passive zone I have given it as tab zone. So this is my active reaction zone, that is battery zone, and the passive zone is tab zones. And then I have done their workbench meshing only in this case, but if you want to prefer fluent meshing, you can go with the fluent meshing also. So mesh, this is my cylindrical mesh, okay. And you can see what we need to have minimum 3 elements and the node to node proper connection. So this we get inside the share topology with help of. Now I'll show you the setup also, but Fluent is running, so I cannot open that window. But you can see I have run it for some time. Okay, this is for some transient case. Now when I do transient simulation, I can check with respect to time. So this is like some time 86.87 minutes. Okay, so if I click apply, it will show the result at the 87-minute time. So you can see the temperature will change. So now the minute temperature is 29 reached to 31.1 degrees Celsius. If I go with 95, apply, the temperature will further increase. So 29, 31. So like 120, apply. So you can see there is a changes are coming, but they are at micro level. So with respect to that part. So this kind of things we can check in the CFD post, and the contours, temperature contours, the plots, all those things we can check in the with respect to. So whenever we do transient case, it is always preferred to use CFD post for the post processing part. Whereas in our case, if we see this is our CFD post. But in that case, I have imported the mesh file and done the part. So we'll check our current case. So this is temperature, it is going. Okay. So let me show you the results as of now in this. Then I will show you the contour also further. So like this, if you make it run further, you will get the graph. Okay, even if you go to this tutorial, we have used same condition. Okay. So you will get the plot like this of voltage, that is discharge curve of 1C. The temperature you get, they have showcased in the Kelvin. I'm changing it to Celsius, so it will show in me degree Celsius. And then we can do the post processing like battery variable post processing. We can check for the potential, electrode potential, then anode potential, electrode, then battery variables, current phi zone, then temperature. So you can see there is a constant heat transfer. It is not like we are getting highly spot, see, because it is single cell. And then we can check the current density vectors, how the current is flowing. So these kind of things we can also check. So I'm just sharing this link. You can download this file, mesh file, and you can import step by step also. So as of now, we don't have a hotspot here, but we can see the temperature range, what temperature we are getting. So you can see with respect to our ambient condition at 1C rate, I'm getting this temperature. If I further run, okay, so this is one, they have given up to 5C. So they have compared the C rating, 0.5C, 1C and 5C. So you can see when I go with at 5C, the voltage drop is more. Okay. And you can see it is suddenly dropping more faster. And if you see this temperature, this is time step. So in 5C, the red curve, I'm getting my temperature within very less time. So that is, it will heat up. So from this thermal simulation, we can identify like how much time it will take to get high spot temperature and what will the maximum temperature range. So those things will identify whether I should keep my design for 1C, 2C or any particular 5C rating. So those inputs we can identify. When we have complete battery pack simulation, okay, in that we'll get the hotspot. If you are not getting like proper thermal like we are getting here, then means we will get some hotspot. But that means we are not getting proper conduction. So since this is a single model, we'll not get this kind of things. Okay, so you can try this and let me know if you have any question. Then in the next part, we'll cover the thermal pack. Okay, so there is a course. Actually, we are running in many of university EV courses, mostly for MTech students. And for BTech students, we are running the certificate courses for battery packs. So mostly university also doing some kind of 5-day workshop also on the batteries. We already done with some institute. So you can refer for that courses also. Then in upcoming webinar for the part, we'll see the battery pack with respect to cooling, liquid cooling and the PCM cooling. In the third part, we'll see the thermal propagation, like when there is a thermal abuse, car hit, how the gas will leak. So please stay connected with us, and then we'll cover this two part in our upcoming webinar. So this will be on next Tuesday, next week Tuesday, and further next to next week, next Tuesday. So we'll share the link you for the invitation, and we'll cover this part of internal short circuit also, and cooling system, then thermal abuse condition, how the leakage will take place, all those things. So we have one question like how to do the grid independent study. So there is multiple way you can study. You can like here we have the mesh size. So you can what you can do, you can apply the method, insert method, or directly like sizing, select the body sizing, and you can select where you want to refine the mesh. Like grid independent generally apply on all parts. So as of now, I have 1 mm. So if I go click on this P, so it will go to the parametric part. Now you can see symbol. If you go to workbench, we'll see parametric set unit. So we have done the set value. Now here I have the value element size. So I can go up to 0.5, then 0.4. So like this, whatever the value I want to reduce for the element size, the mesh will update automatically. But this is input parametric set. Now I want to check for the output because I want to compare the results. So until the values are not same, not get. So what we do in Fluent, there is a output parameter. I will show you how you can create the output parameter. So you have to go to report definition. Okay. So as of now, this is not solved. You can go to report definition where we created the contour, maximum temperature, and there's an option create output parameter. So if you same way, if you're varying some velocity for the cooling part parameter, then we can create those as an input parameter. Now this is my output parameter. Now if I click on this, whatever the parameter you want to compare to check the results, you can create. Same thing will be reflected in the our parametric set. Now you can see on the right hand side, this is my input, this is my output. So value will get here, and then you can compare the value. You can update and you can see with this much mesh size, I'm getting this much value. So you don't have to do complete setup again and all those things. Simply using the help of parametric set, you can run your mesh independent study also.